Welcome to this screencast about section 4.2, Rolle's theorem and the mean value theorem. Really, Rolle's theorem is a special case of the mean value theorem, so you can consider that this entire section is about the mean value theorem. We've already seen two theorems in AP Calculus AB, the IVT and the EVT, and now we're welcoming a new baby to the family, it's the MVT. So firstly, to introduce the MVT, we're going to look at a definition that's not quite mathematical, but it explains what it is. Between 2 points A and B on a differentiable curve, there is at least one tangent line that is parallel to the secant AB. Let's see on the graph what this means. So we have 2 points AB, and between them there is at least one tangent line to the graph that is parallel to the secant. So let's look at the secant first. And there is at least one tangent line that is parallel to this. I think you can imagine where it is. It's right there. So that's what the MVT says. And really that's all we do in this entire section. We're going to look at special cases. We're going to look at cases that we have to be careful of. Misconceptions and so on, but this is all it is. Now, we want to have a better definition, a more mathematical definition, and instead of talking about the points AB, we're going to want to look at the values on the x-axis. So I also called them AB, and the conclusion of the MVT is going to be that there is a point, a number C between A and B, where the slope of the tangent line is equal to the slope of the secant line. So it becomes like this. If f is continuous on the closed interval AB and differentiable on the open interval AB, then there exists at least one number C inside the interval AB such that f prime of C equals, and here's where we have to think about what it means. F prime of C is the slope of the tangent at x equals c, so we're talking about the slope of this, and we want this tangent to be equal to the slope of the secant. So how do we do the secant? It's just rise over run, and therefore what we need to fill up is f of b minus f of a divided by b minus a. So there's a few additional words here that we didn't discuss. Continuous, differentiable, at least one. Differentiable is different from the IVT and the EVT. For the first two theorems we saw, the function only needed to be continuous, and that was enough. For the MVT, it's special. It needs to be differentiable as well. So the hypothesis, the requirements are a little bit more extended. And then there's this at least one here. We will see examples of why we say at least one. There might be more than one place where a tangent line is parallel to the secant line. There is at least one. That is the promise of the MVT. So, talking about differentiable, we have to be careful when we apply the MVT to make sure that the function we are working with is differentiable on the interval. For example, here we have a function that is the absolute value of x on the interval negative 2, 2. Here are the 2 points. We can draw the secant line, and now if we're looking for a tangent line that's parallel to that, well, we will fail to find one. And why is that? Because there is a sharp turn here. So the function f of x equal absolute value of x is not differentiable, and if that's the case, you cannot apply the MVT, and you cannot conclude using the MVT that there would be a tangent line. If you look at this kind of change in the function, this is not the absolute value anymore. It's not a sharp turn. It doesn't matter how small it is, the turn, but now this function would be differentiable, and we could find a tangent line. But like this, we can't. Like this we can, like this we can't. Here's another example that addresses maybe a misconception. In this graph here that you can draw on your notes, you see that between a and b, the function is not differentiable because there's a sharp turn right here. Now, that means the MVT cannot be applied. However, it doesn't mean that there is no tangent line. All it means is, well, the MVT cannot promise to us that there is a tangent line as we see here. Here is a tangent line that is parallel. It happened, but the MVT could not promise us it would. So if you want to write a few sentences about that, here's what I suggest. Here, the MVT cannot be applied because the function is not differentiable in the interval AB. Still, there exists a tangent line parallel to the secant. We can see it here. The MVT could not promise us that would happen, but it does. So the conclusion of that, if the MVT cannot be applied, it doesn't mean there is no tangent line parallel. It just means we don't know. So let's see an example of a function where we can solve algebraically and find where the value c from the MVT is. So in an exercise, on a quiz or a test or an exam, there would be more here. Here we are in the section about MVT, so I just simplified the question. Find the value of c for f of x equals x cubed in the interval -2, 3. Firstly, we would want to be able to sketch f of x equals x cubed, so think for a second of what it looks like. There it is. So it's the curve here. Here it's flat for an instant. The tangent is horizontal. And then it goes up again. So -2, I put it here roughly, and 3 approximately here. And this is the secant line. So we are looking for places where the tangent line is parallel to the secant line. And maybe you've noticed that there's actually going to be two places. One is somewhere here and one is somewhere there. In order to find these, we're going to start by finding the slope of the secant, so f of b minus f of a over b minus a, and we do a few calculations, and we find that this slope is 7. So it's a very steep slope, even though my sketch doesn't show that. So where does f have slope 7 as well? Where is the tangent equal to 7? We need to find the derivative, and then we want the answer to be 7. So we say 7 equals 3x squared, and we solve. We find that this happens at x equals plus or minus the square root of 7 over 3. I didn't write it here as c, but if you write c equals, that's great too. This is the value c that we were looking for. So there are two solutions. The MVT promises that there is at least one, but maybe there's more. Here's an example that's kind of a word problem that actually uses the MVT. We will see how it uses the MVT because it's worth thinking about, but it's not a key part of this section. Two stationary patrol cars equipped with radars are 7 kilometers apart on a highway. As a truck passes the first patrol car, its speed is clocked at 90. 4 minutes later, the truck passes the second patrol car and its speed is clocked at 80. Prove that the truck must have exceeded the speed limit of 100 at some time during the 4 minutes. So all the units are kilometers and hours. In the problem, here there's 4 minutes, so we're going to want to change that to hours. Now the problem is interesting because we have two data. The truck is going at 90 kilometers per hour, then it's going at 80 kilometers per hour, and we're supposed to prove that it was going at more than 100. So why is that? Well, 4 minutes is 1/15th of an hour. So if we're trying to find the average velocity of the truck, its distance over time, it drove at 7 kilometers in 1/15th of an hour, and we get that the average velocity is 105 kilometers per hour. So clearly, the truck was going slowly, then it went really fast, and then it slowed down again to 80, And in the middle, it was really fast because its average is 105. So therefore, there must be a time where the instantaneous velocity was 105. This is the conclusion that you would get from applying the MVT. So how does it work if we think in terms of MVT? Well, here's the situation. This is the truck as it goes through time. These are the 4 minutes that happen, and this is the distance traveled. So as the 4 minutes pass, the truck is traveling these 7 kilometers. And you can see that it's not going at a constant speed. In fact, it's quite important to realize that the slope is telling us the velocity. At the beginning, this slope here, so the slope of the tangent line at this point here, this slope is 80. Because distance over time, or the slope, is going to inform us about the velocity. Sorry, I should have said it's 90. Here it's 90. Over here, the slope of the tangent line at the end is 80. So I tried to make a sketch where the slope at the beginning was a little bit steeper than the slope at the end. Obviously, in real life, a slope of 90 would be extremely steep, but I just wanted to point out what's going on. So imagine this slope is 90, this slope is 80. Now you can see that in the middle, we could pick any point here to get the instantaneous velocity. And we notice that here the instantaneous velocity is very high because the tangent line is very steep. So the MVT says that if we draw the secant line between the beginning and the end, we get the average velocity, and we find 105. This is the 105 we found. So somewhere along the graph, the tangent line, there is a tangent line that has the same slope. In fact, there are 2 places where the truck was driving at 105 according to my sketch. And in between it was driving even faster. So to conclude, Rolle's theorem is a special case of the MVT, and it's a special case. That means you can always apply the MVT and it'll work. Rolle's theorem is the same for when the 2 points are exactly at the same height. So f of A is the same as f of B. Let f be a continuous function on a closed interval AB and differentiable on the open interval AB. If f of A equals f of B, then there is at least one number C in AB where f prime of C equals, it's exactly the same as the MVT, but what happens when f of A equals f of B is that the secant is horizontal. So the conclusion is there is a place where f prime of C equals 0. Here's the secant, it's horizontal. My sketch isn't perfect, so A and B don't look like they're quite at the same height, but they should be. And here's the value where f prime of C equals 0 as well, because it's horizontal, it's parallel to the secant line. Notice that there's other places where there's a horizontal tangent, here and here, but these do not count for the MVT. The MVT promises us that there is a parallel tangent line inside the interval AB. If it happens elsewhere, well, fine, but that's not what the MVT is talking about. So if there's a question about finding where there's a tangent line that's parallel according to the MVT, and you answered here it is, that would be wrong. Okay, I think that's it for this section. Thank you.